Hello, everybody. Welcome to the Fast Code Seminar. Today's talk is one in a monthly series of virtual talks on the latest topics in the theory, practice, and teaching of software performance engineering. My name is Bruce Hoppy, and I co-chair the organizing committee for the Fast Code Seminar. And I lead community outreach for the larger Fast Code project, of which the seminar is a part. Before Kuba introduces our speaker, I'd like to take just a minute to let you know about the Fast Code Seminar and the larger project. I put the link to fastcode.org into the chat, and I'm sharing the screen so that you can see the landing page, the welcome for the Fastcode open source ecosystem. That's a community dedicated to advancing software performance engineering. And so you can see a number of different ways in which we do that related to research and technology and education, skill building. Featured events especially include the Fast Code Seminar, and you can see today's talk. Next month, we're going to be featuring Andrew Chen and David Glake. I'm not sure how to pronounce his name. So put that on your calendars. And previous seminars, most of those are recorded. And a big thanks to the rest of the organizing committee, which includes Kuba, Roberto Palmieri, Christian Schultz, Julian Shun, and Yihan Sun. In addition to things like the Fast Code Seminar, Fast Code ecosystem includes a newsletter and a blog. And I particularly want to encourage you, if you have any work that you'd like to make more accessible to a broad audience and get them interested in software performance engineering, I would love to talk with you and help publish a blog post about whatever you think is really interesting and exciting about software performance engineering. For example, recently we had a talk about energy efficiency, which is different than time, which is something we often think about. So there's a lot going on in Fast Code, and thank you for showing up. And that's all I'm going to say for now. And I'm going to turn it over to Kuba to introduce today's speaker.
Thank you. Thank you, Bruce. My name is Kuba. I'm a research scientist at Google. And today I have the pleasure of introducing Laxman Dhulipala. Laxman is a professor at University of Maryland and also a part-time research scientist at Google Research. He specializes in high-performance parallel algorithm. And one thing Laxman does particularly well is combining theory and practice. So the algorithms he works on have often come with very rigorous theoretical analysis, and on the other hand, not only he's providing very efficient implementation of those, he also picks problems to solve that have very strong practical motivation. And in recognition of his work, Laxman received Paris Kanellakis Theory and Practice Award 2 years ago. He also received several Best Paper Awards, including 2 Best Paper Awards at SPA. Laxman has been, for me, the person that brought me into parallel algorithms work, and a person from whom I learned a lot. And so, without further ado, I would like to give the floor to Laxman.
Thanks so much, Kuba. Thanks for the introduction. I was actually Kuba's intern at Google Research way back in 2018. So, and it's a pleasure to keep working with Kuba. Can everyone see my slides?
Yes.
Okay, perfect. And yeah, if I can't see the Zoom chat, so if there are questions, please just stop me and ask. So let me get started. So today I want to talk to you about scaling parallel algorithms to massive data sets using multi-SSD machines. And this is the title of a paper that we actually had at SPA last year, but it represents kind of an ongoing line of work that we're doing in my group. So this is work with Peter, Hao-Hong Lee, Jamshed, who's now at Northeastern, and more recently with Quentin, who's another one of my students. And some of the code we have available is already on GitHub here. More of it will be available in the near future. So let me just give you very quickly a little bit of background about me. So as Kuba mentioned, I'm at the University of Maryland. I also work part-time with Google Research. And the work I've done in my PhD and also recently has been broadly on kind of building scalable parallel algorithms. And one kind of cross-cutting theme through everything has been graph processing. That started when I was an undergrad working with Guy Blalock and Julian Shun. They got me into graph processing, and I'm still pretty hooked. And I'm still working on this. And as graph processing used to be a really big thing in the early 2010s. Now people have kind of shifted, but graphs are still very important. And so graphs still appear in some more recent topics of recent interest, like parallel clustering and approximate nearest neighbor search, which you might have heard about. And those are things that my group is still working on. So yeah, I got my PhD at CMU in 2020, and I've been at UMD since 2022. And I work with a wonderful group of PhD students here. And so to jump into the talk, one question that has been asked by many different and answered partly in many different research papers in our community. For example, by this nice work by Frank McSherry and his collaborators on the scalability at what cost paper, is how powerful is like a single computer or a single multi-core machine. And the question back then was, well, do you really need like a distributed system to analyze your data sets, or will a laptop suffice? And what we saw in the cost paper was, you really don't need such a souped up cluster of machines to analyze pretty large data sets. You could do it with just a single laptop. So during my PhD, Guy, Julian, and I, we also kind of took some steps to understand this question in more detail for graph algorithms. And what we showed in a nutshell is that for a lot of non-trivial graph problems, you can solve them in practice on the largest publicly available graphs while using theoretically efficient parallel algorithms that are derived from the cumulative effort of the past 4 decades of parallel algorithms research. And so a number of the problems that we considered in this benchmark suite are listed here. I'm not going to read through them, but there's a lot of them, and you can see our code on GitHub here. And this is a paper from 2018, right? So at this point, it's almost a decade old. But the results we got are, I believe they were impressive at the time, and I think they're still very good. And I haven't seen many results significantly beat these. In a nutshell, what did we get? We showed that on graphs with hundreds of billions of edges, this is, at the time, it was the largest publicly available graph data set, and I believe it's still either the largest one or close to. You can solve all of these problems in a matter of between seconds to minutes. So you can get BFS, for example, in like a dozen seconds. And for some more sophisticated problems like strong connectivity, computing the strongly connected components, you can solve them in a handful of minutes. And so I'll come back to this at the end of the talk, but I'm actually motivating this to motivate something that's a bit unrealistic now, maybe. And that's this assumption that in this talk that your graph fits in DRAM. So to apply these algorithms, we need to actually have enough memory to store not only the graph, but also some like auxiliary data that is being used in the course of our algorithm. So unfortunately, in 2026, DRAM is not really cheap anymore. And this assumption that we made about big graphs or big data fitting in memory, while it's still possible, you could have like a 26 terabyte DRAM machine if you have enough sockets and you have dense enough DIMMs. It might just not be practical for cost reasons. Not all of us are married to billionaires, and I can't afford such a machine. And the reason this is happening is due to AI demand, AI capex, and you've probably read about this, or maybe you've even experienced it firsthand if you're trying to build a server. But this is a trend we have to deal with, but data hasn't stopped growing, right? So, assuming this trend continues and we're not going to see a decline in DRAM prices in the near future, what do we do? Well, if you have some budget, instead of spending it on DRAM, you could spend it on disks, right? So this is actually some prices my student found on Amazon. This is what Peter found. This is about a year ago. So he got a 64 gigabyte DRAM kit for like $150. So with the same amount of budget back then, you could either buy 64 gigabytes of DRAM or 8 terabytes of disk. And just to show you what happened in the past year, right now, this a similar kit would be about $500. And a similar, if you spend the same amount of money on a drive, I'm sorry, this is the wrong picture, but you can get like a Seagate Exos drive with like 18 terabytes for about the same amount of money. So recent trends have only kind of tilted this comparison in favor of using hard drives or not using DRAM. So what happens? What changes when you use hard drives? This is called the external memory setting. And this is a setting that was kind of extensively studied in the 80s to 90s. And it was an active research area then. It's still a somewhat active research area. And what you could do in principle is just use these external memory algorithms. You store your entire graph on disk, and you use these external memory algorithms to handle extremely large data sets with low cost. However, these algorithms in practice, because you're using disks, tend to be kind of slow. And the reason is you're using disks, right? And despite decades of effort on improving disks, we do have improvements in reliability, but the fundamentals of disks haven't really changed. You're still getting sub-gigabyte per second read and write throughput. But there has been another technology that's emerged, solid-state drives, SSDs, and this is a trend that's emerged over the past 2 decades, and that technology still does see significant improvements in bandwidth from generation to generation. And unlike disks, they support random reads and writes with reasonable granularity. So that would seem to offer some advantages. So let's just look at a comparison between disks and SSDs. So if we use the same kind of $500 budget, you get about a 64x improvement in capacity from going from RAM to SSDs. But compared to disks, you get less capacity, but the bandwidth improves a significant amount. Right? So the only problem is that on our servers, using DRAM, you can get about 145 gigabytes per second of bandwidth out of these RAM sticks. Now, obviously, you can't do that with just like the configuration I showed you. You need more sticks of RAM than 2 in order to get that bandwidth. But with a single SSD, you're limited by how much bandwidth that single SSD can support, which is about 7 gigabytes per second, optimistically, if you're not running out of like the on-device cache on the SSD. So what do you do? What could you do? Well, a very natural idea is to just, how do we scale a single DIMM up to such a large bandwidth? We add more DIMMs. So why not try doing the same thing with SSDs? Let's just add more SSDs and replace RAM with SSDs. So what if we attach multiple SSDs to a machine? And each of these SSDs in principle gives us about 7 gigabytes per second of bandwidth. And these are numbers that are from PCIe Gen 4, which is now at least a generation old. I think PCIe Gen 5 has become more broadly available. And in principle, the more SSDs you kind of add on, the higher your aggregate bandwidth would get. So you could go up to a very large amount of aggregate bandwidth. So this seems straightforward. What's challenging? But what changes? A lot actually has to change. So first, how do you actually attach a lot of SSDs to a machine? What if your machine doesn't have enough PCIe slots? How do you attach them? How is data going to be stored on the SSDs? How is it accessed, right? What interfaces do you use for reads and writes? Do you treat it like a raw block device, or do you mount a file system on it? Do you access all these SSDs separately, or do you apply RAID on them and kind of treat them as a single external memory device? And those are just some of the high-level considerations. There's a bunch of other kind of low-level configuration parameters. There's something called IO-MMU, and you have to kind of carefully go through these choices because selecting the wrong choice can cause significant performance problems until you figure out you did something wrong when you were setting up your kernel. And these are some of the kind of foot guns you can shoot yourself with a foot with when setting up this like multi-SSD system. And then on the algorithm design and implementation front, once you've actually kind of built this machine, how do you program it? Do you just take existing shared memory algorithms and run them on a multi-SSD setup? And that seems kind of tricky at first glance because, unlike in memory where reads and writes kind of load a cache line, maybe 64 or 128 bytes at a time, on SSDs, you need to load at least 512 bytes or 4096 bytes, depending on the exact details of your SSD on your hardware. And even if you do adapt your algorithm to take advantage of IOs at these small sizes, you have to worry about the CPU overhead that performing these IOs consumes, right? So if you're trying to produce a large number of these IOs, it will cost a large amount of CPU overhead. And additionally, we still, even though SSDs are good for random IO, we still kind of prefer sequential IOs to some degree. And finally, SSDs, each SSD has some amount of internal parallelism. So if we just issue one read or write to an SSD at a time, we will not saturate the bandwidth for that SSD. So this raises the following questions that we had. So, I just gave you this laundry list of challenges. We had the same questions when we were starting this work, and we wanted to kind of undertake this exploration. So we wanted to build one of these machines and show that you can take external memory algorithms, well-studied external memory algorithms, and show that when you implement it properly on multi-SSD machines, you can get running times that are almost as fast as highly optimized shared memory counterparts. So throughout this talk, the main question is, how fast can we go with multi-SSD machine? If we take an algorithm and run it purely in DRAM, what's the penalty we pay when we offload much of the data to multi-SSDs? So that's one kind of question, right? So if you compare an in-memory analytic versus multi-SSD, well, what's the penalty we pay? And the second is just a scaling question. By using multi-SSDs, can we scale to much larger data sets than we could have analyzed purely in memory? So we built one of our own multi-SSD machines to try and answer some of these questions and to have some fun. So here is some details about our machine. So we built it with one of these kind of high-end desktop Threadripper CPUs. So it's not something that you would necessarily stick inside a server in a data center, but it's a powerful consumer-grade CPU. And we bought about 512 gigabytes of DRAM. So it's a high-end desktop. At the time, this cost about $10,000. I think if you did it now, I didn't do the exact calculation, it might be about $20,000 to $25,000. And that's because both DRAM and SSD prices have gone up. We bought 31 SSDs, which I think was overkill. We didn't need so many SSDs, but I'm happy that we have them now. And these all get attached to this machine using the PCIe interface. And the reason we picked this particular CPU and the motherboard that we're using is it exposes a very large number of PCIe lanes. So if you're building one of these machines, it's critical that you not only buy a CPU, but you also buy a motherboard that exposes enough of these PCIe lanes. Otherwise, you won't be able to connect all these SSDs up. Or you might be connecting them in some suboptimal way where there are too many connected on some small set of PCIe lanes. So each of these lanes is giving you about 2 gigabytes per second of transfer speed. That's a theoretical supported speed. So the theoretical maximum on this particular setup is 256 gigabytes per second. So in principle, you might hope you would get that. And can you actually achieve that on a real machine? So this is what the machine actually looks like. It's kind of fun to set it up. This is in my office. You basically attach these SSDs to the computer using something called a PCIe splitter, which is what you're seeing on the left here. So you're not plugging each of the M.2s onto the motherboard directly. You're kind of first doing this bifurcation through this 16-wide PCIe lane. And then this PCIe splitter then splits it into like 4 wide lanes to each of the M.2 SSDs. Okay. So each of these splitters has 4. And so this captures 28 of them, and the remaining 3 SSDs are actually put directly onto the motherboard. So we reserve one of these SSDs for the operating system, and so the remaining 30 of them are for running our experiments. And okay, so I said that one of these SSDs gives you about 7 gigabytes per second of bandwidth. So although we're not going to get 256 gigabytes per second, maybe we can actually achieve 210 gigabytes per second of throughput. But unfortunately, even this is too good to be true. And unfortunately, we get a lower bandwidth. We're limited at about 135 gigabytes per second. And we see that writes are a little bit slower and more inconsistent than reads. And these benchmarks were conducted with the Theo benchmark written by Jens Axbo, which is very well optimized. He's also the implementer of IOURAN, which is a library that we're going to use later in the talk. So we see that the scaling kind of stops around 135 gigabytes per second, and we're unable to go higher than this. This experiment was done with 4 megabyte reads, which are large, and basically we're not going to be CPU bottlenecked with such large reads. So what are the bottlenecks that prevent us from getting higher performance? Why couldn't we get 210 gigabytes per second, which is what you would get if all of your SSDs are achieving their peak bandwidth? Well, here are some of the reasons. Here's like a subset of them. And the most important one, I would say, is just the memory bandwidth we have on our machine. So the main limiting factor is that main memory transfers on our machine are limited at about 145 gigabytes per second of bandwidth. This is the third row on this table here. And to read data from SSDs, what do we need to do? The data is not in memory, so we need to move it from SSDs to DRAM. So there's some, potentially that link is a bottleneck. But once you get it there, you need to actually write it into DRAM. And there's no way you can do this faster than your DRAM bandwidth. Another thing I should say is once you go, okay, so the DRAM bandwidth is like one limit. There's also a difference between kind of what you get in microbenchmarks and what you get in real code. So the 135 gigabytes per second that we got is from this Theo microbenchmark, which has some assumptions. It's not really a practical workload you would experience. It's written by an expert. We're not Jan's Expo, so maybe we would not get such high performance. So we wrote our own microbenchmark. We wrote a reader algorithm that is fitting. I'm sorry, go ahead. Sorry, was there a question?
No, sorry, I coughed.
Oh, sorry. Okay. So yeah, this reader we wrote is a more realistic kind of example of what you would do in an actual program where you have a bunch of files split across these SSDs, and your reader is just reading them and trying to get as high bandwidth as it can. But still, 120 gigabytes per second is not bad, and it's quite close to memory bandwidth. And so, one question is, well, this reader is a bit unrealistic. All it's doing is reading this data from SSD into DRAM and then dropping it on the floor. It doesn't do anything with the data. So for a real program that actually processes this data in some way, can we still maintain 120 gigabytes per second? Can we still get this when we're running a useful algorithm? And unfortunately, the answer there is also no. So this is a bit pessimistic. So we compared to a very simple parallel algorithm, probably the first textbook parallel algorithm you would study, which is an in-memory reduce. We compare our multi-SSD version from in this library we wrote called Plaid to the in-memory version from ParlayLib. And Parlay is a very well optimized in-memory suite of parallel codes. It's able to get about 120 gigabytes per second. So not fully saturated memory bandwidth, but getting quite close. And by comparison, our external memory version can only process data at about 60 gigabytes per second. This is about half the performance of the in-memory version. However, you can see that on the very right side of this plot, we're able to scale using Plaid in this blue line all the way up to 2 to the 48 byte integers, which is more than 1 trillion elements and 8 terabytes of data. And you could do this in a very reasonable amount of time, like about 100 seconds. And the in-memory version would definitely not be able to handle this data size. I realized when I was preparing this talk, one thing to try is just to mmap this data and to see if the in-memory version can do it. And that's an experiment I plan to do. I suspect that it would have some significant performance overheads over what we're doing, but that's an experiment I plan to do. And so one question is, why is there such a large performance gap here? What prevents us from actually matching the speed of the in-memory version in the cases where the in-memory version actually works and the data fits in memory? And unfortunately, the culprit, again, is limited memory bandwidth. So let me dissect this a little bit for us. So what do we need to do for each piece of data that we read in a reduce? Let's think about what Parlay's reduce needs to do. It basically performs a single memory operation. It reads some data that's in memory into the CPU cache. So that's a single memory operation. And there's great locality, so we get full utilization of the cache lines we're reading from memory. But what happens on the external memory side, where not only the data is not in DRAM, so we have to do something called a DMA, or a direct memory access. There's a DMA engine that's taking data from the disk and first loading it into RAM, and that eats up some of our bandwidth. And after that's happened, the data is still not yet in the CPU cache, so we need to do an additional read from RAM into the CPU cache. So every cache line that we're accessing, or every page that we access that gets transferred to the CPUs, requires kind of 2 memory operations, which is why we get capped at 60 gigabytes per second. And this is some inherent memory bottleneck that we have in algorithms that are kind of dealing with data on SSDs. So I hope that was clear. If not, please feel free to ask me questions. But okay, a 2x slowdown is not terrible, right? Okay, if it allows us to avoid spending the cost between SSDs and memory, it's about a 30-to-1 ratio right now. Okay, you can get 30 times more SSD, so you get 30x more gigabytes for your dollar than you do for memory if you spend the same amount of money on SSDs and DRAM. So maybe a 2x penalty is not so bad. I have this belief, but. So you're saying at this point, well, this is just for some very simple parallel algorithm, like a 2x overhead, fine. What about for a more complex algorithm, a more complicated workload? Let's see what happens and go through the design of a more sophisticated algorithm. And in our spot paper from last year, we looked at kind of the next maybe pedagogical algorithm you would study, which is a sorting algorithm. So instead of looking at merge sort, parallel merge sort, or parallel quicksort, we looked at samplesort, which is actually a practical algorithm that people run all the time in parallel workloads. So having a multi-SSD version is quite interesting. And the characteristics for sample sort are quite different from reduce. There's a lot more going on. There's sampling. There's writes, unlike in a reduce. So if you've never seen sample sort before, let me go through it kind of quickly. So what does it do? Sample sort is kind of like a multi-pivot quicksort. We first oversample some pivots from the data. So if we want to split into B buckets, we do some oversampling and then winnow those down into just B pivots, B minus 1 pivots that define B buckets. And then we go over all of the elements, the unsorted elements, binary search them into the pivots, and basically identify which bucket each element is falling into. And then we store them into these buckets, and then we sort each bucket and then concatenate them back together to get the sorted output. Okay, so that's sample sort at a high level. And let's think about each of these steps in the multi-SSD setting. Let's starting with sampling. Okay, so each, if you're doing sampling, due to oversampling, we might need to collect millions of samples. For example, if you're processing like 8 terabytes of data, you might need 100,000 pivots, right? And if you do oversampling, you're going to need millions of those samples. And each of those samples is going to require 1 disk I/O. So if we want to retrieve 1 8-byte integer from disk, we would be wasting a huge amount of bandwidth because we have to remember, we access things in the SSD at like at least a 512-byte page level. And typically the page size is 4 kilobytes. So we'd be wasting so much of that by just reading 8 bytes and throwing away everything else. And this is quite different from kind of the sequential scan that we do in reduce, where there we were reading at a 4 megabyte block granularity, and we used all of the data that we read. So I want to show you that small I/O is costly, but it's not terrible because SSDs are actually very good for supporting a very large number of I/O operations per second. So this benchmark here is run using FIO. This is the benchmarking tool I mentioned earlier with 4 I/O jobs. And you can see that at smaller I/Os, at an I/O size of about 16 kilobytes, you're paying a lot in terms of CPU overhead. And the bandwidth is also correspondingly smaller. However, once you get up to a reasonable, all the way up to like a 1 megabyte read, you can saturate the bandwidth and also minimize the CPU overhead. And that's because these I/Os require a bit more bookkeeping. But because you're issuing larger I/Os, you have lower CPU utilization. You can actually saturate the bandwidth. And I'll come back to this experiment a little later. So let me tell you how we actually handle the small I/O case for sampling. We do this using a library called IOUring. So IOUring is a way of dispatching reads and writes to a device, an external memory device, like SSDs. And the nice thing is that it works not only whether the SSD is mounted as a block device or whether there's a file system on it. And the thing that really limits you when you're programming with SSDs like this, or disks even, is the overhead of performing system calls. And IOUring is one way to work around this. It's basically a library that lets you perform a large amount of bashed IOs while performing fewer system calls. And the main idea in IOUring, and also what gives it its name, is to use these ring buffers that are kind of shared, that cross the boundary between the application and the kernel. So whenever the application wants to perform some IOs, it places its requests for those IOs inside of this ring buffer. And then it performs a single system call that tells the kernel, hey, I got a bunch of these IOs I'm trying to perform. Please process them for me. So basically, it increments some counter that then now the kernel knows there's some new IOs. So the next time the kernel comes and checks this ring buffer, it can take all those IOs and dispatch them to the SSD for us. So basically, this is letting you batch IOs. And because you have so many fewer system calls, you can drastically reduce the amount of CPU time you spend performing system calls. The library is not without its complications. It's kind of a tricky thing to program with, but once you program with it a bit, overcome issues like with alignment and things like this, you can get really excellent performance with IOUring. So to summarize, for these kind of throughput-oriented applications, like everything I'm talking about in this talk, it makes sense to use something like IOUring. You should pay the cost once to learn this and to build low-level interfaces in your code to use IOUring. And hopefully, once you do it once, you can kind of reuse this across a bunch of different parallel algorithms. And the benefit is it lets you batch IO requests and get really high bandwidth without much CPU overhead. So as one data point that I'll again come back to a little later, this was not using FIO. We actually wrote our own microbenchmark that was able to get, across all of the 30 SSDs that we have, we were able to get 27 million IO operations per second using 4 kilobyte reads, which are very small reads. And so this is actually coming from a real piece of code that we wrote. And this is super promising, right? So if you're trying to run some kind of irregular parallel algorithm, something like a graph algorithm, this result that you're able to like almost saturate the SSD bandwidth with 4 kilobyte reads and get such a large number of IOPS is pretty encouraging. And it suggests that even for irregular or data-dependent parallel algorithms, you could still get good performance on multi-SSDs. Okay, so I've introduced IOU-ring. I haven't shown you any code. I've kind of hand-waved, but I don't think I would want to in a talk unless we had a lot more time. So with this kind of detour on IOU-ring finished, let's think about sampling again. Based on the result I just showed you, if you could do 27 million IOPS, you don't need to worry about sampling. You could just do random reads for the sampling, and they will take a negligible amount of time. So that handles it. Just use IOU-ring, do very small, like 4 kilobyte reads, and that solves the problem. Well, what about the other steps in a sample sort? The next step, step 2 in sample sort, is to actually do the partitioning. So what are we going to do? We're going to read a large chunk of unsorted elements from disk, and we need to take each element in that big read and binary search it over the pivots and spill it into one of these buckets that it's going to go to, and then kind of dump that element to some file for that bucket. So we need to aggregate these elements into maybe some buffers. And how would you actually implement this, right? Each worker is maybe like aggregate. It has a number of buffers proportional to the number of buckets, and then once the worker's buffer fills up, you would send it to the disk, right? Maybe you have some mechanism to append it to a file, right? And you could do this in some coordinated way across the threads. So how large should these buffers be, right? Again, I'm showing you a result that I've kind of shown in the table. Let me walk through this, right? So in order to get good bandwidth, right now we're doing writes. We don't want to do writes at too fine a granularity, because we kind of said earlier that we really prefer large IOs over smaller ones. So the reason is this experiment that we ran showing this plot here. So this is another Theo microbenchmark that's using all the SSDs. And the only thing there's a lot going on in this plot. The thing to pay attention to is this purple line. And the purple line is showing you the bandwidth, the write bandwidth that you're getting as you increase the block size. So for a very small block size, you don't get very good write bandwidth. This is what I showed you in the table earlier. But once you get up to like a 256 kilobyte block size or a write size, you basically saturate the bandwidth of these SSDs. And the blue line here, the blue line with crosses, is the CPU utilization you have, the amount of CPU overhead that you pay. So, at 256 kilobytes, you still pay something non-trivial in terms of the CPU overhead. You'd really like to go up to like a megabyte or 4 megabytes to have kind of negligible CPU overhead while still saturating the SSD bandwidth. So the takeaway from our perspective, we're trying to write these like throughput-oriented applications, is we'd like to organize our writes into large enough chunks that we can do ideally 4 megabyte writes to the SSDs. And that would ensure that we have low CPU utilization and we're not spending a lot of CPU doing writes. We can save our CPU to do other things like binary search or actually sorting these buffers. However, if you make these buffers too large, like 4 megs or even 2 to 6 kilobytes, and you have every thread having a number of buffers proportional to the number of buckets, you're going to quickly run out of memory. So for example, if it's 4 megabytes, the total number of buffers you need is the number of threads times the number of buckets, and then multiply that by 4 megabytes. That's quickly going to become a very large amount of memory. I think even for 2 to 6 kilobytes, it's going to be something like 40 gigabytes or 35 gigabytes or something. So we need something to address this. So instead of kind of having every thread have its own per bucket buffer, we have a 2-level buffering scheme. So we first have the threads buffer into these 4 kilobyte buffers, and these are per thread buffers. So there's one of these 4 kilobyte buffers per bucket. And then we pay a penalty of a small amount of synchronization to aggregate these 4 kilobyte buffers into a global structure that's kind of collecting them into these larger arrays of writes that are going to happen to a single file. So we buffer up a large number of these 4 kilobyte writes, say until we get at least 4 megabytes of them, and then we perform a single large flush And IOU ring turns out to have some internal APIs that actually let you do this without wasting a lot of copies. So you can basically take pointers to a number of kind of 4 kilobyte blocks, and without copying them into a contiguous portion of memory, you can actually flush these and perform them and treat them as though it was a single contiguous buffer that's all going to get appended to a single file. So that's very nice. We don't have to waste the memory bandwidth kind of copying and flattening these buffers.
So
Sorry, go ahead.
just a quick clarifying question. So it comes out of I spend a lot of time programming SSD drive algorithms, so although not like yours. The the question I have, you're talking about the IOU ring interface, but if you actually look at the drive, there's an interface, usually an NVMe interface there. And are you going to talk about the queuing there, or are you just assuming that the IOU ring sort of insulates you from that?
I'm assuming that IOU ring and the fact that we're spreading our data and our writes across these large number of SSDs is going to insulate us from this. So I'm working at a slightly higher level of, I'm not thinking about the low level NVMe interface. I'm assuming that we're kind of like dispatching enough writes to the SSDs that we can saturate their bandwidth, and we'll have a large enough queue depth basically for these SSDs that we don't have to worry about whether we're saturating them or not.
No, I thank you. That clarifies everything I need clarified. I realize there's a lot more you could have studied, but this is great.
Yeah, no, I completely agree. So this is, I would say my expertise is not in SSD programming. I'm still very much a novice, and I'm learning, and it's fun. But if anyone else feels there was something naive or something interesting to look into in this study, please reach out to me. I'm very happy to take any feedback or suggestions for things to look into. This is very much still an ongoing active area of research in my group. And yeah, feel free to interrupt if you have other questions, okay? So this is kind of what's going on at a high level. There's a lot of other kind of tricky implementation details to get right. But for the purpose of this talk, I'm going to present it at this level. And again, in a nutshell, what are we doing? We're adding a small amount of synchronization overhead to globally coordinate, with this kind of global structure. And this helps because now we can have much smaller buffers and also scale to a much larger number of buckets without blowing up our memory budget. So finally, the last step is sorting in memory. And this is probably the simplest step. You basically just take one of these buckets from disk, and the buckets are split up into these like large file chunks. Again, I'm hand waving some details here. And what are we going to do? We're going to take that bucket, load it into memory, sort it in memory, and then write it back to disk. And if you designed a better CPU sorting algorithm, or maybe one that's better taking advantage of SIMD or something, you could just plug it in here at this step and speed up the overall algorithm. And we have some IO module abstractions that we wrote that let you do this in a pretty clean way without worrying about the low-level details. That's actually true for the entirety of this sample sort algorithm. So overall, the sample sort code we wrote is about 100 lines of code. And we actually are abstracting out quite a lot of the multi-SSD details into some lower-level interfaces that deal with IOU ring. So this kind of points the way at possibly some higher level of abstraction for programming these things, but I don't want to oversell what we're doing. It's still very messy, and we're still often writing IOU ring code from scratch per application, as I'll show you in a little bit. So how does this algorithm perform now? Recall our goals.
Laxman,
I'm sure.
There's a question, I think, from Kuba.
Mm-hmm.
Yeah, so I'd like to understand like this abstraction part, because so far you've been presenting this as if there was like a one drive, but actually there are multiple of those SSDs. And so, for example, when you measure the bandwidth or the IOPS, do you somehow need to ensure that they are evenly distributed across different disks, or is there something that provides you this in a transparent way? How do you make sure that you're not like hitting all the one disk with all of those operations?
Perfect. Yeah. So this is like a load balancing question that you have to kind of think about per application. For something like sorting, we assume that the input data set is kind of sharded across all the SSDs, right? This is similar to how you shard like a RDD, like a redundantly distributed data set or something, right? So we basically just partition it evenly across all the data set, all the disks. And then the output that we're generating, the sorted output, is also going to be kind of sharded in this way across all the disks. So in order to get the sorted output, you have to actually, you can logically think about concatenating all the files on the disks. Each of those files is sorted, and you spread them across the disks this way. Does that answer your question, Kuba? But I think a different application, for example, in graph applications, that I'm going to talk about in the second part of this talk, you have to be very careful, right? You don't want to have a situation where all of the IOs are happening on a single small set of files that are all stored in a single SSD, because that could very quickly become the bottleneck for your program.
So in particular, like whenever you're running those benchmarks, you do have to manually ensure that the locations are spread across different drives. Is there something that provides you with this spreading, or is it something that you also have to implement manually?
This is something we implemented in our library. So the data, there's some data file plumbing that will handle this kind of thing kind of transparently for you. But it's something that we had to handle, right? There's no other tools or abstractions, unless you're using something like RAID 0. RAID 0 is basically taking the disks and striping your writes across the different disks. And that comes with some software overheads. That's something else that we need to explore in this space to show kind of the performance penalty that you get by using RAID 0. We do have some experiments showing that there is a non-trivial penalty, but I haven't included them in this talk. There's still some things that we're working on. Did that answer your question?
Yes, thank you.
Okay.
I think there was another question, actually.
Yeah, go ahead.
Yeah, I'm slightly repeating the previous question, but it seems to me like the fundamental baseline you'd want to compare against is RAID 0 with mmap. That configuration requires no coding changes at all. Obviously, It's going to be slower, but the key question is how much slower?
Good. I don't want to say a number that I get incorrect. If you send me an email, I will go dig this result up. We did run this once. I don't remember exactly. It is measurably, it is like significantly slower. You have especially when you're doing this with like 30 SSDs, the overhead of software RAID is high. Unfortunately, I don't remember the number now. You could do something like hardware RAID.
That's what I was going to say. Maybe not on your configuration, but certainly in a server setting, you would go with hardware RAID 0.
Absolutely. I'm kind of thinking some of this is like, I'd like to see other labs, like maybe bioinformatics labs or people that build like this kind of server, not like necessarily data center grade hardware. I think you could build one of these things and analyze like incredibly large bioinformatics data sets. And so I'm assuming that maybe they don't want to pay for hardware RAID, because those things, to my knowledge, I think hardware RAIDs, those modules are pretty expensive. But it's a very reasonable question. And again, I'm just scratching the surface of this exploration. That's a question that we should look into in the future.
Great, thank you. Thank you.
Good. So let me go back again. So for this comparison and everything I'm doing in this talk, it's always comparing in-memory, highly optimized in-memory algorithms versus multi-SSD algorithms. So our goals were we should be able to handle very large data sets and incur minimal performance loss against a well-optimized in-memory algorithm. So how do we do? Here's our sorting results from samplesort. And you can see that there's some reasonably large overhead that we're paying at the very beginning. And this might just be some overheads for initiating IO. But once we get up to like reasonably large input size, like 2 to the 34 8-byte integers, or 128 gigabytes of data, there's only a 20% difference between us and the highly optimized in-memory version from ParlayLib. And that's something that's used in a lot of other parallel codes. And unlike the in-memory version, which eventually runs out of memory, our algorithm keeps scaling pretty gracefully, and it scales all the way up to sorting 2 to the 40 8-byte integers across our 30 SSDs. And this is exactly what we wanted to show at the beginning. So that's great. Now you're wondering, well, if you want this kind of result, maybe you have to build the same machine that we did, right? Do you need to build this costly and labor-intensive machine and put it all together? We wanted to also show that our program and this model more broadly is portable, and it's not something super esoteric that we built, right? Of course, if you go to server grade hardware, you do get rackable, like, I don't know, 2U servers or something like this that have an insane amount of SSD slots. So if you're willing to buy server grade hardware, you could buy a multi-SSD machine that just provides this kind of platform for you. And indeed, instead of buying it, you can also rent one of these things on the cloud. So in order to show it's portable, we ran some experiments on a cloud machine. This is a Google C3 cloud machine. And this is a machine with 32 SSDs. Each of them has less capacity and also much less I/O bandwidth. So you're getting about 10 gigabytes per second of I/O bandwidth. And I can confirm that they're actually achieving this. And you can rent one of these machines for about $10 an hour, which is pretty inexpensive in order to get a very large amount of storage and potentially analyze them in very large data sets. So in terms of I/O bandwidth, they're a little bit under provisioned compared to what we have on our machine, but maybe this is actually like a better balance. And it turns out that this is actually enough for sorting. So here's a table showing the performance scaling on both machines. And so whenever we're going down a row, the data set size is doubling. So we go all the way from 8 gigabytes of data all the way to 8 terabytes of data. So our results on the 30 SSD machine are on the right-hand side. And we can see that for larger data sets, what we see is the running time kind of more than doubles. So when you go from scale 35 to 36, it goes up by a little bit more than a factor of 2. And the reason is that on our machine, we have ample I/O bandwidth, but we're bottlenecked by CPU. And we don't have enough CPU power or CPU cores to kind of do all the work that we need to do in the binary search step and also in the bucket sorting step. So when the data set size doubles, the work slightly more than doubles. And so the running time also slightly more than doubles. However, on the C3 machine, you can see that it's much closer to just straight doubling, right? When you're going up from one scale to another. The running time almost exactly doubles. And that's because the C3 machine is bottlenecked by I/O. So I think our two machines are kind of on either sides of this sort of perfectly balanced point. And so although there are, I guess the point from this experiment is that the bottlenecks on both machines are slightly different. But maybe like a broader takeaway is this algorithm and this model and the setting that we're working with is quite portable. And I'll show results now on graphs on yet another GCP machine called a Z3 machine. So it's, I guess my point and my hope is that you realize that you can access these machines today and you can start programming with them today. And I'm really hoping that more people will work on writing algorithms for this type of hardware. So what are some of the takeaways so far? If you read and do nothing with the IOs, all you're paying for is a DMA, you can get really high bandwidth, like 135 gigabytes per second, but this is not super useful. If you do some lightweight operations on the reads and writes, like in the reduce, then you can get between like a half to a third of the performance of in-memory only algorithms. And the memory bandwidth of kind of reading the writes to SSD, to memory from the SSD becomes the bandwidth, right? So you're still bottlenecked by memory bandwidth. Now, if you're not memory bottlenecked and you're CPU bound, like in sorting, then you can match in-memory performance. You can get within like 20%, even with pretty limited I/O bandwidth. And the amount of I/O bandwidth you need kind of depends on exactly what type of application you have. And although I think we massively over-provisioned the amount of I/O bandwidth we needed on this machine, it's a good test. It's still a good test bed for kind of testing these things. And I don't know if you remember, but on this plot showing the scaling, the bandwidth scaling as a function of the SSDs, we were scaling comfortably up to like 16 or so SSDs. So I think if I had to go back and build this machine again, I would probably stop at around 16 SSDs. I don't know if we needed all 30 of them. So in the last part of this talk, I want to kind of talk about some ongoing work we're doing on problems that are not so nice as reduce and sorting. So what about like irregular graph algorithms? Things like tree traversals or graph algorithms. Is the multi-SSD model and is this setting still a good platform for programming such applications? So what are the challenges? I've already kind of enumerated some of them, so let me go over this kind of fast. Think about a graph algorithm. Every time we want to fetch and process the neighbors of a vertex, you need to basically do some load. In memory, that load of the neighbor list is going to be one or a couple of cache misses if it's a reasonably low degree vertex. In an SSD, just loading that neighbor's that neighbor list is going to cost you a single, like a block read, a 4 kilobyte read, and most of the data is going to be wasted, right? So the total I/O that we do is going to potentially dwarf the number of bytes that we actually consume. And again, just like in the in-memory setting where we have this issue with DMA, we're already kind of starved for memory bandwidth. And one might think that like in these irregular problems, they're even more bandwidth hungry, right? They're even more bottlenecked by memory. So for the rest of this talk, I just want to look at the BFS problem and see how well we can do. So very quickly, if you haven't seen or studied in-memory BFS, there's a line of work that started in the early 2010s that optimized in-memory BFS. And one of the main optimizations for in-memory BFS is this so-called push-pull optimization. And if you think about how a BFS works, you have a frontier. That's the set of a parallel BFS. You have a frontier of vertices that are being expanded to the next frontier. And you could do this in one of two ways. And this is the switching between these two things is what's called the push-pull optimization. So in one setting, you're going over the edges incident to the current frontier. That's all these red edges here, expanding them and finding the next frontier. And this requires you to process all the edges incident to the current frontier. Now, when you pull, you go over all unvisited vertices, all vertices that have not yet been reached in the BFS. And each of those vertices reads its in edges and checks whether that neighbor, that in neighbor, is in the previous frontier, or if it was basically already visited. If it was, you know it's in the previous frontier, and now this vertex will be in the next frontier. And the nice thing is, well, once we find one edge like this, you can stop. You don't need to keep going over the remaining in neighbors. So if you enable this pull-based optimization carefully, you could potentially drastically reduce the number of edges you inspect, because these vertices, maybe they're able to find an in neighbor quickly and avoid scanning all of their in neighbors. So that's what this plot here is showing. You can see there's this sort of, in real world graphs, you often see this phenomenon where the size of the frontier kind of grows and becomes very large in the middle of the execution, in the middle of the BFS, and then becomes smaller later. So for these rounds where the frontier is very large, enabling the pull optimization is often a good thing to do. And you could do this even in a way that is theoretically efficient. Okay? So this ends up being a critical optimization for in-memory BFS. And again, the reason is, if you haven't seen this before, the reason is it lets you look at potentially much fewer than m edges, right? All the edges in your graph, because for many vertices, when you process them in this pull phase, they will only scan a couple of incident edges and quickly find a neighbor in the previous frontier. So is this optimization also helpful on multi-SSDs? Turns out, yes, it's very helpful. Let me quickly, I know I'm going to run out of time soon. Let me go through how we do this. So we use something called a semi-external memory model, a semi-external graph algorithm model. We basically assume we have enough DRAM to store all of the per vertex data in DRAM. So we can store things like the frontier, a visited bit array, or the distances. And we assume like a ratio of DRAM to SSD between about 1 to 20 and 1 to 40. And if you think about this argument I made about prices between DRAM and SSD, if you spent an equal amount of money on DRAM and SSD, this is exactly how you would provision your machine. So I think it's a reasonable thing to assume that you have this ratio. How do we store our graphs on SSD? So this is a very natural format. I think it's it's surprisingly natural, but I haven't seen anyone doing exactly this. But I'm not claiming any novelty here. I think if you thought about this, you would come up with exactly this format. Okay. So here's what we do. We have a array mapping all the vertices to blocks. And these blocks are stored at the 4 kilobyte page granularity. And vertices are stored in consecutive blocks. So for example, if you have a high degree vertex, you would store it on some number of consecutive blocks. This is like at the logical block level. And then you map these logical blocks to physical blocks using some kind of load balancing strategy. You could either do round robin, which is what we're doing in our initial experiments. You could also try hashing them for load balance. Maybe you can benefit from some kind of balls and bins analysis. Okay. So hopefully that part's clear. You map the vertices to blocks. There can be multiple vertices in a block if the vertices are all low degree. If the vertex is high degree, you spend multiple blocks on that vertex. And then you encode the blocks using some kind of block format. And the block format, well, what do? It's basically like a compressed sparse row layout in miniature. We store basically the number of vertices, the ID of the smallest vertex, and the degrees of those vertices locally within the block. So it really does look like a compressed sparse row layout in the block. And we additionally allow the blocks to be encoded in different types of formats. So we support, obviously, uncompressed. You can store the neighbors using ints. We support delta encoding, and we also support something called delta plus interval. Interval is a type of like a run length encoding, where if you have deltas that are all like 1, 1, 1, 1, 1, or 2 to 2 to 2, you can store them as a single interval. Right now, we're only handling consecutive IDs, but we're planning to extend this to also run length encoding, which is something we did in Allegro Plus. So these are classic ideas in graph compression. Nothing new going on here, just putting together well-known pieces. Now, how do you do IOs? I'm going to go over this very fast. Okay, so we, again, do the most natural thing. We take the frontier, we group it by the block that the vertices are trying to access, the block that their neighbors belong in, and then every worker has its own IOU ring, and this is where there's some IOU ring details, and we had to carefully engineer this. There's a bunch of details I'm sweeping under the rug. But basically, every worker will buffer up some number of block reads it's trying to do, and then submit them to the kernel. And then once it reaps the system call, it reaps its ring, gets the data, it processes the block and decodes the block. It only processes the edges for vertices that are kind of marked as active in the current frontier. So this is, if you're familiar with how in-memory graph processing systems work, this is taking ideas from kind of highly optimized in-memory graph processing systems and just making the IO substrate work for like a multi-SSD setting. Okay, so we're basically just doing the IOs for multi-SSD and then trying to reuse as much of the in-memory infrastructure and ideas as we can. Now, what about for dense traversals or pull-based traversals? Instead of scanning the entire graph, we do one additional optimization where we kind of coarsen the granularity into 512 kilobyte chunks. So you coarsen the graph into these larger chunks, and for each chunk, you keep a bitmap saying whether there's an unvisited vertex still left. So initially, every chunk will be marked active, and eventually these chunks will become like deactivated. And this helps you avoid some large reads that you can avoid doing when you're doing the dense traversal. And in order to make the dense traversal fast and very bandwidth efficient, we do it at these 512 kilobyte reads, which has low CPU utilization, and you could saturate the bandwidth here. Okay. Let me quickly show you the results. So we did it. We ran our algorithms on these big graphs, including this hyperlink 2012 graph. We ran it on this Z3 machine. It has 12 SSDs, each supporting 3 gigabytes per second read-write. First takeaway, okay, if you go to var_int plus interval, you get really impressive space savings. So on ClueWeb, I hadn't run interval on this graph before. You get a 10x space savings over uncompressed by using the var_int delta plus the interval format. And one open question here is, can you get a better do faster encoding for this interval format? It's a little bit slow right now, but we have some ideas for how to speed this up. Reducing the amount of data, the data footprint, directly reduces the running time. So if you go from uncompressed, you get that 10x reduction in IO in data size gives you about a 6x reduction in the end-to-end running time of our BFS. Okay, and finally, we compared this with the in-memory BFS in the graph-based benchmark suite. This is the stuff I showed you at the very beginning of the talk. And if you compare apples to apples, if you compare the var_int delta format, which is what GBBS uses, there's only about a 1.3 to 1.5x penalty on the large graphs. It's a slightly larger penalty on the smaller Twitter graph, but I think what we care about are the large graphs. And I personally feel that this is a surprisingly small penalty to pay. I'm still surprised at how low the penalty is comparing an in-memory irregular graph problem like BFS compared to like its corresponding multi-SSD execution. So let me wrap up. There's some other slides here. Feel free to email me for the slides. I won't mention this now. I think the main next steps are to port this for all the other graph problems we have in GBBS. And potential future work is extending this to dynamic graphs, extending this to other irregular problems that have modern relevance, like these ones I mentioned in the beginning. And what about other types of analytics, not just graph problems, like key value stores in multi-SSD? Are there applications where you have to do a very large read in a small amount of time, and actually striping or kind of reading from all the SSDs simultaneously would yield better latency? If you have ideas of applications you think might benefit from this setting, please email me. I'd love to chat. So to conclude, it looks like we can now run algorithms on really large data sets at a small performance loss with very low cost using multi-SSDs. And the next piece of work now is to validate this with more case studies, to make it easier to program, and to build software libraries that let people program and translate their in-memory algorithms to multi-SSDs easily, right? And these problems would have been prohibitively costly to solve with in-memory algorithms. One thing we want to show is that you could scale this up to like trillion edge or 10 trillion edge graphs using our techniques. I believe we can. And the slowdown we're getting, it seems like a fair trade-off, given that we can significantly reduce the cost of purchasing a machine that still analyzes such a large data set. And so, multi-SSD seemed like a good way of handling the growing challenge of processing large data in the age where DRAM is just impossible to buy. So thank you for coming to my talk. And our code's all available on GitHub. We'll put the graph code up on archive soon, in probably the next 2 months or so. And I'm very happy to hear from you if you're interested in working on some of these problems or you have some ideas. I'm happy to talk.
Thank you, Laxman. And
Thanks. Are there any
fantastic.
questions? I know we're a little bit over time.
We're just past the top of the hour. So does anybody have any kind of a closing question? And we can take a question if anybody wants to help us close today's seminar.
Yeah, I have a small question. So in GPU accelerated machines, people are building a lot of multi-SSD kind of systems where you also have direct I/O into the GPUs. So you're not even limited kind of by PCIe bandwidth. You might have like an NVLink directly from your SSDs into your maybe 8 GPUs on a node kind of system. Probably you could even get higher bandwidth than what you're getting on these PCIe systems. I'm wondering if you think maybe similar ideas apply, or you might want to do something different. Those kind of machines, you could maybe port these graph processing frameworks to those kind of systems too. Do you have any thoughts there?
Thanks for the question. Yeah, it's something that I've been aware of. I know that people are doing this to do like offloading, to run MOE models like at on huge parameter models, right? I mean, people are doing some very cool things there. I haven't seen anyone doing this type of work using that hardware. And well, maybe one reason is that it's very expensive. But if you did have access to this hardware, and unfortunately I don't, I would love. I think that's a very nice idea. I think you could take a lot of these ideas, and there are some very well optimized GPU graph processing codes out there. There's the Gunrock library that John Owens and his group has at Davis. There are other advancements that people have done in recent years. It'd be super cool to see people showing how to do GPU graph algorithms or GPU irregular algorithms and do offloading to SSDs in the same way, in a similar way that we're doing. I think the programming model would have to be a bit different. It's probably very NVIDIA specific. I'm sure you had to use like NVLink or some libraries around that. But I kind of have a feeling that a lot of what we're showing here would be applicable, and probably you could get very similar results on the GPU, but it'd be much faster because you have much better bandwidth, as you said. So thanks. I mean, if someone in the audience is interested, they should definitely look into that. It seems like a good project to look into. Cool.
Thank you for the question. Oh, and is the comment here? No, I just see applause and thanks in the chat. And we are just a little bit over time. So if there are other questions, I encourage folks to just reach out to Laxman offline. And once again, Laxman, thank you very much for presenting at the Fast Code seminar today. That's going to wrap up today's seminar. And we would love to see you in June for the next seminar. Thanks again, everybody.
Thanks so much for hosting us, Bruce. And this is a great thing that you're doing. So thank you.
Pleasure. Bye.
Bye.